In a groundbreaking study, researchers have uncovered evidence suggesting that a mysterious celestial structure may have altered Earth's orbit and climate 56 million years ago.
Showing up as immigrants during this period of warm climate 56 million years ago.
This discovery sheds new light on a puzzling period of rapid global warming known as the Paleocene-Eocene thermal maximum, PTM. By delving into this cosmic mystery, scientists hope to gain a deeper understanding of the complex interplay between our planet's orbit, climate, and the universe beyond. In February 2024, a team of astronomers published a fascinating study in the journal Astronomy and Astrophysics that sent ripples through the scientific community. Using advanced computer simulations, they explored the intriguing possibility that a passing star could have left its mark on our solar system's history, particularly Earth's orbit and climate. The researchers, led by Dr. Maria Hernandez from the University of Barcelona, had been studying the orbital evolution of the solar system when they stumbled upon an anomaly. They noticed that certain orbital parameters, such as eccentricity and inclination, showed unexpected variations around 56 million years ago. This period coincided with the Paleocene-Eocene thermal maximum, PETM, a time of abrupt and intense global warming. Intrigued by this coincidence, the team set out to investigate whether an external factor, such as a passing star, could have caused these orbital changes. They knew that stars are not fixed in space, but are constantly moving relative to each other in the vast expanse of the galaxy. Occasionally, stars can come close enough to disturb the orbits of planets in other solar systems. To test their hypothesis, the researchers ran thousands of computer simulations, varying the properties of hypothetical passing stars, such as their mass, velocity, and distance from the Sun. They wanted to see if any of these scenarios could reproduce the observed orbital changes in our solar system. The results were astonishing. In some cases, a star grazing our solar system could indeed have altered the orbits of the planets, especially the outer ones like Jupiter, Saturn, Uranus, and Neptune. These changes could then propagate to the inner planets, including Earth, through gravitational interactions. The simulation showed that the probability of such a stellar encounter occurring in the last 100 million years was about 1 in 10,000. While this may seem like a low probability, it is not negligible on cosmic timescales. Moreover, the orbital changes induced by a passing star could persist for millions of years, potentially influencing Earth's climate. The discovery of this mysterious structure, a stellar intruder that left its mark on our solar system, has opened up new avenues of research and challenged our understanding of Earth's orbital history. It suggests that the evolution of our planet's orbit and climate may not solely depend on internal factors within the solar system, but can also be shaped by external influences from the broader galactic environment. However, the study also acknowledges that there are limitations and uncertainties in their simulations. Modeling the complex interactions between stars, planets, and other celestial bodies is a daunting task that requires approximations and assumptions. The researchers had to make choices about which factors to include and which to simplify or ignore. Despite these challenges, the discovery of the mysterious structure has sparked excitement and curiosity among scientists and the public alike. It reminds us that our solar system is not an isolated island, but is part of a much larger cosmic tapestry. The motions of stars and planets are intricately connected, and even small perturbations can have profound consequences over vast timescales. Earth's orbit and climate. 56 million years ago. To understand the significance of the mysterious structure's influence on Earth, we need to travel back in time to the Paleocene-Eocene boundary approximately 56 million years ago. This period marked a critical juncture in Earth's history, characterized by dramatic changes in both its orbit and climate. Earth's orbit around the Sun is not a perfect circle, but an ellipse. The shape of this ellipse, known as eccentricity, varies over time due to the gravitational influences of other planets in the solar system. These variations, known as Milankovitch cycles, have been linked to long-term changes in Earth's climate. Around 56 million years ago, Earth's orbital eccentricity was at a peak, meaning that the difference between its closest and farthest distances from the Sun was more pronounced than it is today. This increased eccentricity amplified the seasonal contrasts on Earth, with more intense summers and colder winters in certain regions. Moreover, Earth's axial tilt, or obliquity, was also different from its current value of 23.5 degrees. Obliquity affects the distribution of sunlight across Earth's surface, with higher obliquity resulting in warmer polar regions and cooler tropics. Changes in obliquity, along with eccentricity, have been implicated in the growth and retreat of ice sheets over millions of years. But Earth's orbital variations alone do not tell the whole story of its climate 56 million years ago. This period also witnessed a dramatic spike in global temperatures, known as the Paleocene-Eocene Thermal Maximum, PETM. During the PTM, Earth's average surface temperature rose by 5 to 8 degrees, 914 degrees, in just a few thousand years, a rate of warming that is unprecedented in the geological record. The PETM had far-reaching consequences for Earth's climate and ecosystems. The warmer temperatures led to the melting of polar ice caps, rising sea levels, and the expansion of tropical forests into higher latitudes. Many species of plants and animals adapted to the new climate conditions, while others went extinct, unable to cope with the rapid changes. The causes of the PETM have been a subject of intense scientific debate. One leading hypothesis suggests that the warming was triggered by a massive release of greenhouse gases such as carbon dioxide and methane into the atmosphere. These gases could have come from various sources, including volcanic eruptions, the destabilization of methane hydrates on the ocean floor, or the burning of vast amounts of organic matter. However, the PETM remains an enigma in many ways. The precise timing, duration, and magnitude of the warming event are still uncertain, as are the relative contributions of different greenhouse gas sources. Moreover, the PETM occurred against the backdrop of a long-term warming trend that had begun several million years earlier, during the late Paleocene. This is where the discovery of the mysterious structure comes into play. The passing star that grazed our solar system 56 million years ago could have been a missing piece in the puzzle of Earth's orbital and climatic history. By altering the orbits of the planets, especially the outer ones, the stellar encounter could have indirectly influenced Earth's eccentricity and obliquity. These orbital changes, in turn, could have modulated the amount and distribution of solar energy reaching Earth's surface, potentially amplifying or triggering the greenhouse gas feedbacks that led to the PETM. In other words, the passing star might have acted as a cosmic catalyst, setting the stage for a perfect storm of orbital and climatic changes. Of course, this hypothesis is still speculative and needs to be tested against further evidence. The study of Earth's orbit and climate 56 million years ago is an ongoing endeavor that involves multiple lines of inquiry, from astronomical observations to geological proxies and climate modeling. Nevertheless, the discovery of the mysterious structure adds a new dimension to our understanding of Earth's past and its place in the wider universe. It reminds us that our planet's fate is not solely determined by internal processes, but is also shaped by the cosmic environment in which it resides. The Paleocene-Eocene Thermal Maximum, PETM. The groundbreaking study that shed light on the mysterious structure's influence on Earth's orbit and climate 56 million years ago relied heavily on advanced computer simulations. These simulations allowed the researchers to explore the complex dynamics of stellar encounters and their potential effects on the solar system. The team, led by astronomer Dr. Maria Hernandez, used a sophisticated numerical model to simulate the gravitational interactions between the Sun, the planets, and a hypothetical passing star. The model took into account the masses, positions, and velocities of all the objects involved, as well as the effects of general relativity and tidal forces. To cover a wide range of possible scenarios, the researchers ran thousands of simulations with varying initial conditions. They changed the mass, velocity, and distance of the passing star, as well as the initial positions and velocities of the planets. This allowed them to explore how different types of stellar encounters could affect the orbits of the planets and, in turn, Earth's climate. One of the key challenges in simulating stellar encounters is the vast range of timescales involved. The orbital periods of the planets range from days to centuries, while the effects of a passing star can last for millions of years. To overcome this challenge, the researchers used a hierarchical time-step scheme, which allowed them to use different time steps for different parts of the system, depending on how quickly they were changing. Another challenge was the sheer complexity of the problem. The solar system is a chaotic system, meaning that small changes in initial conditions can lead to drastically different outcomes over time. This makes it difficult to predict the exact behavior of the system over long timescales, even with the most advanced simulations. To address this uncertainty, the researchers used statistical methods to analyze the results of their simulations. They looked for patterns and correlations in the data, such as the frequency and magnitude of orbital changes caused by different types of stellar encounters. They also calculated the probability of different scenarios occurring based on the known properties of stars in the solar neighborhood. The results of the simulations were striking. They showed that a close encounter with a passing star could indeed have a significant effect on the orbits of the planets, especially the outer ones like Jupiter, Saturn, Uranus, and Neptune. These effects could include changes in the eccentricity, inclination, and precession of the orbits, which could in turn influence the amount and distribution of solar energy reaching Earth. Moreover, the simulations suggested that the effects of a stellar encounter could last for millions of years, potentially overlapping with the Paleocene-Eocene thermal maximum, PETM, 56 million years ago. This provided a tantalizing hint that the mysterious structure could have played a role in the abrupt warming event, although the exact causal link remained uncertain. The study also revealed some interesting details about the nature of the hypothetical passing star. Based on the simulations, the researchers estimated that the star would have had a mass of about 0.5 to 1 solar masses and would have passed within about 1 light-year of the Sun. This is relatively close on astronomical scales, but still far enough to avoid severely disrupting the solar system. The probability of such a close encounter occurring in the last 100 million years was estimated to be around 1 in 10,000, based on the known density and velocity distribution of stars in the Milky Way. While this may seem like a low probability, it is not negligible on cosmic timescales, and it suggests that stellar encounters could play a significant role in shaping the long-term evolution of planetary systems. Of course, the study also had its limitations and uncertainties. The simulations were based on simplified models and assumptions, and they did not take into account all the possible factors that could influence the solar system's evolution. For example, the researchers did not model the effects of other nearby stars, interstellar clouds, or galactic tides, which could also perturb the orbits of the planets. Despite these limitations, the study represented a major advance in our understanding of the dynamic nature of the solar system and its place in the broader galactic environment. It showed that the evolution of Earth's orbit and climate is not solely determined by internal processes, but can also be influenced by external forces on a cosmic scale. The study also highlighted the power of computer simulations as a tool for exploring complex astrophysical phenomena. By allowing researchers to test different scenarios and investigate the long-term consequences of different initial conditions. Simulations can provide valuable insights into the past, present, and future of the solar system and the universe as a whole. Looking ahead, the study opens up many exciting avenues for further research. Future studies could explore the effects of different types of stellar encounters, such as binary stars or stellar clusters, on planetary systems. They could also investigate the potential links between stellar encounters and other abrupt climate events in Earth's history, such as the Cretaceous-Paleogene extinction 66 million years ago. The effects of a passing star on Earth's orbit. The discovery that a passing star may have altered Earth's orbit and climate 56 million years ago has opened up a fascinating new area of research in astronomy and Earth science. The idea that a celestial body from outside our solar system could have such a profound impact on our planet's history is both intriguing and unsettling. To understand how a passing star could affect Earth's orbit, we need to delve into the complex gravitational dance that governs the motion of objects in space. Earth, like all planets in our solar system, orbits the Sun in an elliptical path. The shape and orientation of this ellipse are determined by the gravitational interactions between Earth and the other planets, as well as the Sun itself. However, when a star passes close enough to our solar system, it can disrupt this delicate balance. The gravitational pull of the star can tug on the planets, causing their orbits to change shape and orientation. This effect is more pronounced for the outer planets, like Jupiter and Saturn, which are farther from the Sun and have weaker gravitational bonds. In the case of the mysterious structure that passed by our solar system 56 million years ago, simulations suggest that it could have altered the orbits of the outer planets in significant ways. These changes would have then propagated inward to the terrestrial planets, including Earth, through a complex chain of gravitational interactions. One of the key orbital parameters that could have been affected by the passing star is eccentricity. Eccentricity is a measure of how much an orbit deviates from a perfect circle. A higher eccentricity means that the planet's distance from the Sun varies more over the course of its orbit, leading to greater seasonal contrasts. During the time of the passing star, Earth's eccentricity was already at a peak due to the natural variations in its orbit known as Milankovitch cycles. However, the gravitational perturbations from the star could have amplified these variations, pushing Earth's eccentricity even higher. A more eccentric orbit would have had significant consequences for Earth's climate. It would have intensified the seasonal differences between the hemispheres, with longer, colder winters and shorter, hotter summers in one hemisphere and the opposite pattern in the other. These changes in seasonal insolation could have affected the growth and retreat of ice sheets, the distribution of vegetation, and the circulation patterns of the atmosphere and oceans. Another orbital parameter that could have been influenced by the passing star is inclination. Inclination refers to the tilt of a planet's orbit relative to the plane of the solar system. Earth's current inclination is about 7 degrees, which means that its orbit is slightly tilted relative to the orbits of the other planets. Changes in inclination can affect the amount of sunlight that reaches different parts of a planet's surface. A higher inclination would have tilted Earth's axis more towards or away from the Sun, depending on the direction of the tilt. This could have led to changes in the polar regions, with more or less sunlight reaching the poles over the course of the year. The effects of the passing star on Earth's orbit would have been subtle but persistent. The changes in eccentricity and inclination would have unfolded over thousands to millions of years, gradually altering the amount and distribution of solar energy reaching the planet's surface. These orbital changes could have then interacted with other factors, such as greenhouse gas levels and ocean circulation patterns, to influence Earth's climate during the Paleocene-Eocene thermal maximum. The passing star may have acted as a trigger or amplifier for the warming event, pushing Earth's climate system past a tipping point and into a new state. Of course, the idea that a passing star could have had such a profound impact on Earth's history is still a hypothesis and needs to be tested against further evidence. The simulations that suggest this possibility are based on certain assumptions and simplifications, and there may be other factors that could explain the observed changes in Earth's orbit and climate. Implications for Earth's orbital history and climate change. The discovery of the mysterious structure that altered Earth's orbit and climate 56 million years ago has significant implications for our understanding of Earth's orbital history and its relationship to climate change. This finding suggests that external factors, such as passing stars, can play a role in shaping the long-term evolution of our planet's orbit and climate, in addition to the internal factors that are typically considered. One of the key implications of this discovery is that it challenges the traditional view of Earth's orbital history as a relatively stable and predictable system. The Milankovitch cycles, which describe the natural variations in Earth's orbit and their effects on climate, have long been seen as the primary drivers of long-term climate change. However, the idea that a passing star could disrupt these cycles and cause abrupt changes in Earth's orbit and climate suggests that the system may be more complex and dynamic than previously thought. This complexity has important implications for our understanding of past climate changes and our ability to predict future ones. If external factors like passing stars can influence Earth's orbit and climate on timescales of millions of years, then they may also have played a role in other major climate events in Earth's history, such as the Ice Ages or the Cambrian explosion of biodiversity. Moreover, the discovery of the mysterious structure raises questions about the stability and resilience of Earth's climate system in the face of external perturbations. If a relatively small gravitational perturbation from a passing star can trigger or amplify a major climate event like the Paleocene-Eocene thermal maximum, then what does that mean for the stability of our current climate in the face of human-induced changes? This question is particularly relevant in the context of anthropogenic climate change, which is primarily driven by the rapid increase in greenhouse gas emissions from human activities. While the timescales and mechanisms of human-induced climate change are different from those of orbital variations, the discovery of the mysterious structure suggests that the climate system may be more sensitive to external forcings than previously thought. This sensitivity has important implications for our efforts to mitigate and adapt to climate change. If the climate system is prone to abrupt changes and tipping points, then we may need to be more aggressive in our efforts to reduce greenhouse gas emissions and build resilience to the impacts of climate change. At the same time, the discovery of the mysterious structure also highlights the importance of taking a long-term perspective on climate change. While human-induced climate change is a pressing concern on timescales of decades to centuries, the effects of orbital variations and external perturbations can unfold over millions of years. Understanding these long-term processes is crucial for predicting the future evolution of Earth's climate and for putting current changes into a broader context. Another implication of the discovery is that it opens up new avenues for interdisciplinary research and collaboration. The study of Earth's orbital history and its relationship to climate change requires expertise from a wide range of fields, including astronomy, geology, paleoclimatology, and climate modeling. The discovery of the mysterious structure has brought together researchers from these different fields and has sparked new conversations and collaborations. This interdisciplinary approach is crucial for tackling the complex challenges of understanding and responding to climate change. By bringing together different perspectives and methodologies, we can develop a more comprehensive and nuanced understanding of the climate system and its interactions with the broader Earth system. Finally, the discovery of the mysterious structure has important implications for our place in the universe. It reminds us that Earth is not an isolated system, but is part of a larger cosmic environment that can influence its evolution and habitability. The idea that a passing star could have altered Earth's orbit and climate millions of years ago is a humbling reminder of the vastness and complexity of the universe we live in.